And also Arnold with the R. So there's a mathematical method or classical mechanics. They are famous book by for classical mechanics. From all Euler differential equation. Arnold's book is a wonderful book. So at some point I will use the Arnold also the 李斯老师的讲义. That's my plan, and then yeah. So I used to. So previous courses I give like every week, so the homework every week. So 但是现在那个人工智能发展很大，所以如果用人工智能的话，非常容易解决问题，那个作业的问题，所以作业的意义现在不那么大，所以so I only give 5 or 6 homework in this course. So yeah, 5 or 6 homework, not so much. Just to review the course, to to keep your motivation and review the course. So 轻松. So and then so this is the I would say 50%, and then final exam, the 期中考试. So that's the grading scheme. Okay. So that's the case. And then this so this time the course is way like more relaxed than the previous 4 times. So my plan is just my plan is let you enjoy the course and try to develop the intuition of geometry and geometry and topology. So yeah, 我希望大家相信我的这门课。That's the case. So the question and so 如果你有问题的话，你可以问我，在微信群、微信里问我，发给你的邮件也可以，发给我邮件也可以，我在课里也可以问题，什么时候都可以。Okay. So that's any question about this course? Okay. Okay. So the 拓扑和那个几何非常重要，现在物理里面。所以我们要学习这个流行。She is this one? Oh, sorry. Oh my goodness. Yeah, I already can't write the Chinese character. Sorry, let me record. Yeah. So first we learned the manifold and many things. Manifold, 相当讲vector field. And then 斜空间tangent boundary and cotangent boundary. We'll learn this kind of stuff. And later, so we'll learn that differential form, and so on. Differential form, and then we will learn Riemannian geometry next. Yeah, Riemannian geometry. And in relation to GR, I think this time I try to be more talk about the connection to physics too. Physics too. Okay, and then so here differential forms and Brown cohomology. And also later we'll talk about symplectic geometry, basic of symplectic geometry. So this is a relation of transform mechanics. So this is a relation with the generative relation GR. Okay, so that's the case. And later, so after that, we will learn about so these are more like a geometry. After that, we will we will learn the topology. So the homology. Homology 同样 homology and cohomology. So this one is it correct? Cohomology, you should tell me. You should teach me. I will teach the differential geometry. You should teach me the Chinese. Homology, cohomology, group, and the fundamental group. Okay, so 这个被称为基本区。So these are sorry. So the who initiated Riemannian geometry? Who initiated? Of course, Riemann. Of course, Riemann. But many people after that developed that. And then symplectic geometry is more like starting from Hamiltonian, or like Lagrange. So it's a long, the beginning of 19th century. So this is the mid 19th century start. So who initiated homology or cohomology? Do you know? Who initiated? Do you know? So this one, this is the Alejandro Lagrange. Hamilton. And then these are notions. And after that, we will talk about the group, briefly, and the algebra. And then after that, we talk about vector number. So I learned that the Chinese character is shiny and stuff. Oh, but I'm not sure if I can write down only with differential. Oh, yeah. Like this way? Challenge. So back to bundles. So okay. These will play a very important role in some of the Young-Mills theory. So Young-Mills theory. And then, yeah, at the end of the lecture, maybe we talk about so-called characteristic classes. So, for instance, is it correct? Channel is correct. Oh my goodness. Is it correct? Is it correct? But I cannot write down the simplified character. How does it don't share? I forgot. Anyway. So my brain is not already like declining. So somehow I cannot write the Chinese character. I don't know why. Yeah. So these are the roughly the course plan. But I mean the course plan. But yeah, if I have if you change my mind, I will put some new contents in the middle, so that maybe I cannot reach to it. So this time I just try to be a little bit flexible and more relaxed, so that the people can enjoy. So that's the yeah, plan of the lecture. Any questions at this moment? Okay. So then let's do the那我想介绍这个最基本的最重要的不变量重复的不变量就是二维球面two-dimensional surface always two-dimensional surface 球面。Okay, so 那我们开始考虑四面体，四面体，好像if you write 四面体。Yeah. So 今天的课是基本上我的中文的练习。So 四面体有四个地点 vertex 定点顶点 OK 顶点是顶点然后so edges how many edges do you have? 6个 so 这个是龙树 so 龙树 顶点数龙数 ，OK， 然后面数 face。How many faces? 几个 ？4。Okay. Yeah, how can I turn off? Okay. Then I should. Oh, that's way better. OK， 或许面数这个四面体有4个面数，然后 the quantity we are interested in is E 减 B 加 F，so 这个 E B F。Sorry, what? No, opposite. Sorry, I'm sorry. Yeah, I think B plus E plus F, and we can do the computation. 4减6加4等于2。It's like a 小数的。Okay. Now, let's do the,这个例子是正方体6对，这样的。那顶点数是8，龙数是几个龙数？龙数是。sorry, B. I'm sorry, my brain is not working. Sorry. 1, 2, 3, 4, 5, 6. Is it correct? No, sorry. This face. 12. Thank you. F is 6. Okay. And then B minus E plus F is 8 minus 12 plus 6 is equal to 2. Any coincidence? Okay. We can do the same thing for other something called for Hydra. For instance, this octahedron, how do you call it in Chinese? 反面体。So B is equal to 6. E is equal to 12. Okay, again. Like this. So this number is called Euler characteristic. Euler characteristic of surface. Let's call surface S. Euler characteristic. one of the characteristic. It's called 确身数。确身数。So why there always two? Why always two? If you pump up this how to say polyhedra with the 球面, no, 球面. It's two. It's called球面. If you pump up air to this, this material is very soft and pump up air, at the end of the day, so you get the S2. Average 球面 you get. So this is the so this polyhedra can be considered as a solid composition. S2. Those polyhedra. What is the erase? Okay. So 这个Euler 虚形式是最基本也是最重要的不变量。Okay. So this is called topological invariant. Without cutting surface and so on, without doing any surgery on the surface, you can change the shape of this 球面 to 半面体，八面体，或者这个四面体，正方体。但是topology doesn't change. So these quantities for topological invariant. And then from now on, so we will learn how to construct these topological invariant. Let me write down. So these characteristic classes, homology group, cohomology group, or this fundamental group, even drum cohomology, all those are this 互变量. In this way, we will learn. So the two-dimensional surface, we can easily like陈类 even like a Chen is motivated by to construct higher version of the Euler characteristic. So he constructed his famous model called mid-40 something. To construct Chen Lei, so he tried to generalize this Euler characteristics for higher dimensional matter. So this 不变量是非常重要。So we are going to learn from these invariants in the during the entire course. 那其他的球面 曲面。You should tell me this is our 曲面。哦，这是丘面，这个是丘面。然后 contain， 环面，环面是 colors。So this one is essentially the S1. S1 is a circle times S1. Another circle. And people write down T2. T2. Okay. Or 环面。Okay. N 为环面是 S1 to the N. Tn. 那这个曲面的这个视线数，视线数是什么 ？So let me use the color because it's more illuminating. 要打开。Okay. So let's consider this circle. You just cut this yellow circle. Then what you get is something like this one. Okay. If you 切这个环面线 along this yellow line, you get this one. It's called cylinder. I don't know how to call it cylinder in Chinese. 就 Even I don't remember how to call it cylinder in Japanese. Yeah. 我认为我的脑子坏了，现在没有。Next, let's cut this surface along this pink line like this one. Yeah. If you cut pink line like this way, you get this kind of surface. Okay. So you have to identify this yellow line, two yellow line, and also this two 红色的线。You have to identify this 黄色的、红色的， you have to get this point. Now B is 几个点顶点数，这个环面有几个顶点数。This point is this point. Okay? This point is also this point. This point is also this point. And this point is also this point. Okay? Okay? So 我以为这个环面有四个点，顶点，但是只有一个顶点。那龙式是几个龙式？ Of course, yellow. There's two two yellow lines, but they're identified. So the two red lines, they're identified. So there are only two. Yeah. Two long. This is very easy. This rectangle. Gem function. Like this. Okay. So the 正面的这个 Euler 置信数和反面的 Euler 置信数不一样。So therefore, this guy has a different topology from this guy. It's very easy. Maybe look like this. Okay. Another surface is called Riemann surface. Of genus G. Genus G. So in this example, G equals 3. But I don't want to. Okay. So let's consider simplest genus 2. How do you counter this Euler characteristic? So pick a point here and cut the surface like this way. Okay. And then this way. Okay. And then this way. And you can cut the surface like this. Okay. Okay. Let me try if I can write down the cartoon of this. Let me write down. Can I write down? Okay, anyway. Okay, let me try to get the. Sorry, I think I need some help to draw nicely. Let me try. Yeah, so I think I want to write it to successfully write. I prefer this. Yeah, maybe I can just use some color. Okay, and then I use red color to cut this one. So if you cut this surface, what's going to happen is as follows. Let me draw nicely. I'm not sure if I'm going to successful. Sorry, I think I should have opened this file before. Yeah. If I cut like this way, so what's going to happen is as follows. Okay, let me erase. So now I can erase around here. What's going to happen is as follows. If you cut like this way, yellow and then okay, like this way, and then surface is something like this. Yeah. It becomes like this. And then, I'm not sure if you can see, I think the blue and then purple. Let's use blue and purple. This is blue. It's something like this one. And then purple. It's like this. It becomes like this. So if you attach it like this way and this way, you recover this genus T unit, genus 2 unit. So this red one is so I just cut along yellow and the red one to get this. Okay. Now we cut along blue and the purple. Okay. What's going to happen? Can you imagine that? And then maybe I can just do the, I can write down the orientation of the edges. For instance, like this way, and to identify it. So like this way, like this way, like this way, like this way. And I need a yellow. Yellow. I don't know which way is the best. Okay. Maybe like this one. Then to identify this one, maybe you need something like this way. And identify like this one, you need a person like this one. Like this one. And then you get the blue and the purple, you cut. And what you end up with as follows. What you end up with is the blue, yellow, red, no, purple, sorry, purple. Purple. 왜 이거 지금 swallow. I think I made a mistake. Yeah, I made a mistake. It is okay. Become like this. Become like this way. And then what you need to do is that the I call B, C, A, B, A inverse, B inverse, B, B, C inverse, and B inverse. So inverse means I just change the counterclockwise. Clockwise. Okay? And if you identify this blue one and the purple one, you get this surface. This surface. If you're clever enough, you can just use this whatever material which can just which are flexible. You just identify this blue edge and the purple edge, and you encounter this surface. And so on. Okay, so that's what's going to happen. Now, 几个顶变数，only one because this is all the edges here. One, the same. Edges are 拢数，拢数是4个。Base is equal to 1. So B minus B plus F is equal to minus 2. Minus 2. So 反面是这个 genus equal to 1. Genus equal to 1. 反面是 genus equal to 1, which is 这个 order 线性数是0. Okay? And in general, so if you have genus G, Riemann surface, the order characteristic of genus G is 2 minus 2G. In fact, we can just compute. This one is already known like a long time ago. So this is like dates back to Gauss. Those are all the characteristics. So another way to compute all the characteristics is follows. So you introduce so-called vector field on the surface. The vector field 是闪亮场。闪亮场，这个 vector field。This is S2. You put the vector here. Okay. And so on. Okay. So this is a vector field, but so this is North Pole. So this is North Pole is Beijing. Is it correct? Is it correct? Or the same as Japanese? Okay, North Pole and South Pole, Nanji. So the vector, so the length is important. So the vector field, if you write down the vector 响链长，秋面的响链长。So the nose at our nose pole, so there is 0. So the length of the vector field becomes 0. But from there, you just become small, tiny vector fields show up. If you just a little bit away, and then it becomes a little bit bigger once you move to the move out of the nose pole. Okay, and then so if you move around here, so this is exactly cartoon from this one. Okay. So you just looking at the how to say 地球 from the above of the nose pole. Okay. Then count. Oops, sorry. It's always normal to do a circle. Like this. Okay. And then you compute how many times you rotate once you go around this nose pole. Once you go around nose pole. That is called index of 0 of a vector. Okay. The vector field. Okay. 0 of the vector field. So in this case, once you rotate the how to say 2 pi, the vector field is also rotated. So vector field, so you just bring this vector field, and then so from here and from here, here and here and here and here and here and here. So you just rotate in 2 pi. So just bring this vector field into the origin. Just bring to the origin. And how many angles like you rotate? It's just really 2 pi. Okay. So in this case, index of nose poles is equal to 1. How about south pole? Around south pole, everything is moving towards to the south pole. So let's look at this kind of cut. Okay. Oh, by the way, so this index is the 直序. Okay. Oh, I see. So in Chinese, this one. Okay. Then really like towards to the origin. Okay, like this. Now let's look at how many times it rotates. So start from here, it becomes like this way, and next is this one, and this one, this one, this one, this one, this one, this one, like this. So you start from here, you just rotate 2 pi, the counterclockwise. Okay? So it's the same thing. So here is also same. So counterclockwise 2 pi. So therefore index of south is equal to 1. Okay. And there is something called Bunker-Holt theorem. Telling that Euler calculus of surface. Sorry, I think I should call it this one S surface is equal to sum of 0. P is a 0 of a vector field. Index P. In this case, there are two zeros. Okay. And the index has a 1 and 1. So therefore, we get again the same order characteristic. We compute by using this B 减 E 加 F 的公式。Another way of getting the order characteristic for sphere is as follows. You can have vector fields not unique. So there is no spot here. So let's suppose no spot here, and you can write down the following example. So you can let's try to write down. So this is the flow of a vector field, and also here you can have, it's hard to draw, but yeah, let me try my best. Like this one. We can have, so the 0 only appears in non spot, and around here, what's going to happen is as follows. And then again, we cut this red one. Okay, around non spot. And you see what's going to happen. Okay, suppose that the vector field is something like this way. So this way, and this way, and then eventually there is something like a vector field like this way. So eventually, so here it becomes like this way, and then eventually inside, it becomes inside. Do you understand what I mean? Can you see that? So here you just rotate and then just vector field inside of this circle. And then here it becomes really tight, it becomes like this way, and then like this way, and this way, this way, this way, and this way. Okay. So what's going to happen is that this red one, starting from here, become like this one. And then they become like this. Can you see that? Now let's start with from here. How many times it rotate? It just rotate. So this is up and down, and it become up. So it's already 2 pi here. Can you see that? And from there, again, you just rotate 2 pi. Okay, do you understand? So now for this index of this one, of this non-spot is equal to 2. Do you understand? So you just rotate and coming back to 2 pi, and rotate coming back to 2 pi. So even though here 0 only appears non-spot, so index will change. So the order factor is still 2. Okay. 那我们考虑反面的话，小量场，最简单的小量场是这样的。最简单的小量场是这样的。这样的小量场，那没有 zero， 然后我的线性数去0。So which is consistent with this package. That's okay. That's 最简单的小量场，但是我们可以。考虑这样的小量场。Torus is here, and there's also height function. There's a height function. You just function to the torus to, so this is torus to arc. There's a map you can consider. And this point is mapped to this point. This point is mapped to this point. That is, I call it the F is called, let's call H, height function. Height function. I don't know. Height is height function H. And then you consider so-called gradient flow. I will explain what is the gradient flow. Gradient vector field, graph H. So in the electromagnetism, you learn something like a gradient of function f, right? Gradient function. Which this is a generalization. This gradient. So this is a vector field. This will give you some kind of like an electric field or some kind of magnetic field to obtain this gradient using gradient. The similar thing you can on the magnet. The height function is the you just assign this point to this height on this direction. You just put the torus inside R3. And you have a x-axis, x, and a y-axis, and this is z-axis. Okay. And the z-coordinate, you just embed the torus inside this R3, and you just consider the z-coordinate. Or maybe h-coordinate, whatever it's called, okay, z is also. Okay. And then you just consider gradient vector here, which you start at the top is here, okay, top here, and you just have like this to the bottom. So it's like you just spread the water from the top to the bottom, and gravity is the negative direction. It's like you just put the whatever liquid from the top, and then they will flow to the bottom. Flow to the bottom. But something special will happen in the 4 point. One point is 4 point. One is the top point and the lowest point, and another point is here and here. So here you have something like that. Like this way. And vector field is behaving something like this way. And you just bring back to here. And also the opposite point is something like this way. And coming back to here. On the other hand, if you come in here, then you just escape to the something bottom, farther bottom. Okay. And if you go here, you just escape to the farther below. So therefore, if you look at this point, so these 2 points are more like a sphere's example. I'm not sure if I erased them. I didn't erase. So like this way and like this way. So top and bottom is a very similar to sphere. On the other hand, so let me erase the D point. So these 2 points is more like this way. On one hand, on one coordinate here, on one coordinate here, it just becomes sink. China. It's something that behaves like that. So moving inside. On the other hand, the other side is just become forced. It becomes like this one. You understand? And what's going to happen? The other place is something like this. Like this one. Okay, so then let's consider the circle around this field. Okay. So you start with the opposite side, but then it becomes like this way. It becomes like this way and this way. At this point, it becomes towards the zero, and it behaves like this. Okay. So it rotated clockwise. Okay. On the other hand, this one is counterclockwise. Okay. So therefore, so this point here is really this point. Is in, okay, let's call the P and Q here. Let's go N and south, maybe. It's a bit strange, but it's just name. The P case index of P is equal to -1 because it's clockwise. It's a clockwise. You can play the same game in Q here. So in Q, it's the same thing happen, but direction is the opposite, something like this. This is the sink direction, and this is source direction. Okay. And you can do the same computation. This is the Q. And you can do the same computation. You can easily compute this minus one. Last one. This is last one, minus one, and plus one. If you sum them up, you get 0. So this is called gradient vector field of the height function. Okay. Okay. And then if you so yeah, and if you consider something called mole theory, so this is related to so-called mole theory. And then anyway, so it's related to so-called mole index mole theory. And the best book to learn the mole theory is the Mellon's book, of course. Mellon's book. And if you open the Mellon's book of the this mole theory, you can see the following figures. Maybe I didn't print it out, sorry. So recently got busy on something very stupid thing, so I didn't print. I didn't have time to print out. But I think if you open it, you will see the following. So at this point, the point here is somehow equivalent to like this way. Equivalent to this way. And then, so if you have a Mohs index 1, so this is the bottom point. And then, so you can add. So if you have another critical point here, so it's called critical point. So 0 is the 0 of the vector field. You can create so-called one handle like this. One handle. So which is exactly this yellow line, the flow is yellow vector field creation. So okay, why point can be approximated by the disk? So this is disk, right? What is the Euler characteristic of point? What is the Euler characteristic of point? Sure. One. What is the Euler characteristic of disk? Disk is something like this one. Whatever approximation you can do. Let's triangle. How many vertices you have?顶点，一个顶点，3个，有3个楼，或者一个面。So Euler characteristic is 1. And then this is in fact is called the disk is contractible to the point. Contract to a point. Although dimensions are different, it's a contractible. Contract. But if you add something 0 of the vector field, some topology will change. So you just add the handle like this way, which can approximate it like this way, like this. So if you grow some fake handle is okay. Let's do the bit more. We add like this. Handle. You can just roll this part and they become like this. Now our characteristic will change. This is cylinder. Okay. Cylinder, what is the Euler characteristic of cylinder? So this is Euler characteristic of 1. Euler characteristic cylinder is 1. You have a cylinder. You can cut along cylinder. You get like this way. Okay. How many? 这个所以这两个顶点，然后三个楼，然后一个面，所以 Euler characteristic is 0. What does it change? If you add a handle, because of this 0, and if you add the handle, Euler characteristic will change. Let's play the game. Because of this another 0 of the this random vector field, you can add. So this will create another handle like this. Then this is equivalent to like this. If you grow them up, you can see that. What is the Euler characteristic of this guy? So this is 0. What is the Euler characteristic of this guy? Can you compute? This is, so the torus is something like this one. Like this way. And you just get rid of the circle like here. So you just want to like this. So that's the game. Do you understand what I mean? Or the circle is kind of hard to compute all the characters, so let's consider this square. Okay. How many edges do you have? How many vertex do you have? 5. Minus 5. Okay, it's hard to say, but it's plus. Sorry, is it true? 6. Sorry, I think I'm doing something stupid. Should I write that like this way? Yeah. Well, that's one way. Okay, so if you do that, what's going to happen? 1, 2, 3, 4, 5. 5 vertex, and how many? 1, 2, 3, 4, 5, 6, 7, 8. Okay, how many faces? 1 face and 2 faces, right? Am I correct? Yeah. Then this is my point. Okay. You agree with me? This focus Euler characteristic is minus 1. This is minus 1. And you add the, on top of that, it's coming from this 0, and then you just erase this whole here. Then it becomes this, and the Euler characteristic. Okay. This is called handle decomposition. Handle decomposition of the handle by using this height function. Anyway, that's one I wanted to. So this is called Poincare-Hopf theorem. So the order characteristic, so I'm going to show that order characteristic of surface is, did I, right? Yes. This. Okay, so that's done. Any questions? Okay. So now I think it's so-called something called the gas. Important thing is gas bond theorem. And the order characteristic of surface is 1/2 pi. This kappa is called Gauss curvature. For instance, this Gauss curvature sphere S2. So this is round sphere is more like the constant curvature, and the plus 1 kappa is equal to plus 1. And what is the area of the sphere? S2, area of sphere. How do you compute area of sphere? 4 pi r squared, and if it is the unit circle, it's just 4 pi. So if you just kappa is equal to 1, Gauss curvature is 1, and integral by S2, you get 4 pi, and the pitch is equal to 2. Torus is just flat. It's just flat. Okay? So the curvature is 0. There's no curvature. Plug into here, you get 0. Yes. The important thing, this amazing term, Gauss bond theorem, you can consider this kind of, you can embed torus inside of R3 like this one. Okay? And you just consider induced curvature. So then here the torus is more like here it's more like you have a curvature here because it's distorted, right? I think curvature is 2u, is that correct? 2u. So if you invert the Nafamian inside of R3, so the R3's the metric would induce the curvature into the torus. So therefore, at this point, curvature is no longer 0. Actually, at this point, the curvature is positive. In fact, around the inside, curvature is negative. Inside of this red line and the outside the red line, the curvature will change. But if you integrate out all the Gauss curvature on the surface, ultimately it's invariant. It's a very amazing theorem. It's what the Gauss has found. The Gauss is a genius. He's a founder of kind of modern mathematics. And then as we will learn, so this kappa can be computed by using Riemannian geometry. So this is right-hand side is the so-called differential geometry, quantity coming from differential geometry. Left-hand side is called topology. The Gauss bond theorem will connect topology and differential geometry. And what's more is that this kappa is computed by using local data of this point. Each point you can have a curvature. So local. But if you just integrate out all those local data, you get the global information of the circuit. So this Gauss-Bonnet theorem will connect local information to global information. Okay. The Ponger-Hopf is the same. So all those data, index of 0 of the vector field are local data. But if you sum them up, all the index of 0 of the, so this is the right hand side local, but the left hand side is global. So those are the, so the Gauss-Bonnet and Ponger-Hopf is the simplest example, which connects the local data of the manifold to the global data of the manifold. Okay, let's take a break. Yeah, let's take 10 minutes break. 语序物语的中文怎么说？再说一遍。
不希尔规则，中文就是不希规则。
I don't think it's correct. It's correct?
我理解你的担心。如果你指的是数学中著名的不希不等式，那它的中文确切说法是不希不等式或不希尔不等式。我之前误用了规则这个词，抱歉，刚才没准确表达。
No, I want to say Euler characteristics of Riemann surface of genus G is equal to 2 minus 2G in Chinese.
黎曼曲面的欧拉式性数等于2减去2倍的 G， 其中 G 是它的规格。
OK。规格是 genus。
没错，规格指的就是 genus， 也就是曲面的种数或者种类的数目。
那规格 G 的黎曼曲面的有2减2G 欧拉式性数。
是的，没错，
没错，谢谢。规格。曲面的规格 G 曲面的或者式性数等于2减2G 2减2G。规格规格曲面的欧拉式性数是2减2G。活泼。 quick, 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 quick. Okay, shall we resume? Okay. Now let's try to so the genius called Edward Witten introduced, and we will learn that we will learn the time model of this So there's a paper called supersymmetry. So the Witten, 1982, he introduced the mole theory. I did like a super how to say, a super brief introduction of the mole theory. I didn't say anything about what are the moles function, what are the moles index, and so on. But I just give you a rough picture by using this gradient flow to construct the order characteristic. Yeah, if you want, I can talk about mole theory in this lecture a bit more later. Because the last full lecture didn't include mole theory. Anyway, so if you have any like topics you want me to teach, just let me know. I can think some whatever which is not inside this section. Whatever you're interested in, just tell me. I mean, it's a good to include a new topic for me. I mean, I don't want to teach the same material because it's boring. As a timer, so let's consider timer. So this 多元 challenge 非常很大的研究领域，所以最简单的模式，我们考虑最简单的模式。那考虑这个积分。Okay. Suppose the function s is something like this one. So if you change your variable, you get the minus infinity to infinity exponential. 1 from half s squared dx squared. Okay. And then if you use the Gauss integral is something like minus infinity to infinity e to x squared minus sign and dx is fine. It's like this. So therefore this is equal to 1. On the other hand, suppose s this function is something like this one. Whatever. Then this will integral become infinity to infinity. Because s is if x goes to minus infinity, s of x is infinity. X goes to infinity, you get the infinity. Now for infinity to infinity and same integral, it should be equal to z. Now for this integral depends on, suppose s of x is a polynomial in x, so you have x to the n plus lower degree. By the way, how to say polynomial in Chinese? Do, shen. Is it correct? Do, shen, shen. Same as Japanese. Polynomial, the highest degree of the power matters. If it is even, it's infinity to infinity, eventually. If it is odd, minus infinity to infinity. Is that okay? So suppose A is the positive quantity. Okay. Therefore, this C either 1 or 0. Like this one. So now we will do the following. Suppose we scale f of x to t times s of x. And we send t goes to infinity. Okay. Then t is equal to minus infinity to infinity dx to square root and exponential of b. Yes. So now, so t equals to infinity means that this quantity is very big. Exponential minus infinity is what? Exponential minus infinity is what? I'm just trying to check whether you're right now. Exponential minus infinity is what? 0. 0. So if you send the t goes to infinity, most of the integrand it becomes 0. Except this quantity becomes 0. Therefore, what's going to happen is that so except the s of x becomes 0. So if s of x is 0, even if t goes to extend to infinity, the integrand is 0, right? Integrand is 0. Therefore, what's left is here. What's left is here. So therefore, it becomes sum of s of xi goes to 0, and the sign that's awesome. Okay, that's what's going to happen. So only surviving point is at the 0 of this function s, and at that point exponential of 0 is 1, and what's left is this quantity. And then if you rescale the t, so here t goes to infinity, but if you do the correct calculation, what's left is the sign of this derivative. So what's going to happen is that, for instance, if you look at this the white one, so the 0 is here, and the slope here, ds dx, at this point is positive, right? It's positive. It's a positive. This is plus 1. How about here? It's negative, right? It's negative. ds dx is negative, minus 1. And this point is plus 1. Because it just slope is positive. So therefore, this white one will give you plus 1, minus 1, plus 1, which is 1. It's consistent with this integration. On the other hand, for this yellow one, we can have this point is negative, minus 1. This point is positive. This point is negative. Minus 1, this point is positive. And if you then add them up, you get the z, which is consistent with this. So if you just localize all those data, so when t goes to infinity, everything suddenly goes to infinity or minus infinity and so on. So that what's important is left in 0 here. Which is very similar to the program. So very similar. So this integration is just determined by 0 of this function s. So it's very similar to program. Similar to And this can be formed as follows. So this integration, if you introduce so-called Grassmann variable, so rho and chi. I called rho chi. Grassmann means if you swap them, you get the minus sign. That's equal Grassmann variable. You can just write it down as follows. This z as follows. Okay. So if you add z is equal to, we can write down so for the Grassmann variable dx square root 2 pi d chi in the rho exponential minus 1/2 s squared x plus rho ds dx chi. You just write down like this. And if we apply the rule of the d chi, chi is equal to 1, otherwise 0. The same rule for d rho. Like this way. And then in particular, so if you have two integrals, so d chi, d rho, rho chi is equal to 1. Okay. So then if you do the Taylor expansion of this one is equal to this means that so rho square is minus rho square. So if you swap rho square, you get the minus sign. So therefore this means that the rho square is equal to 0. And the same way chi square is equal to 0. That's the new Grassmann variable. And if you do the Taylor expansion of this guy, okay? If you do the Taylor expansion of this guy, this can be written as exponential minus 1/2 s squared of x, and then you have 1 plus rho ds dx chi plus 1/2. Like this. And then we already know rho square is equal to 0 already. Okay. So you can just ignore higher term. Okay. And this one will also vanish because the d chi d rho integral doesn't see anything here. So what's left is this guy, and if we use this rho, if you use this rule, the chi dx like this one. Okay. So this can be understood as something called the path integral. Of understand? Or mass matrix model. It's just integral, but whose Lagrangian is given by as follows. Lagrangian And this has the following symmetry. If you take the Lagrangian del x is equal to chi, del rho is equal to s of x, you get this Lagrangian is invariant. Let's check that. Let's check that. Del R is minus. So if you apply del of s, you get the s of x ds dx and chi plus del rho of ds dx of chi. The rho is s of x. Okay. And then we don't need to talk about del chi, and you just apply del s to the here. Yeah. So even if you apply del s to here, eventually you will pop out the chi here, and because it's the function of x, right? It's a function of x. If you take the del of x, you get a chi here. Okay? And the chi square is equal to 0. Therefore, we don't need to think about del of s, del of chi. Del of chi is equal to 0. So this is it. Therefore, this is equal to 0. So this means that the Lagrangian is invariant. It's invariant. This transformation. And furthermore, it's an important transformation. So this response variable is more like a fermionic quantity, because rho square is equal to 0 means that if you have the same state, same variable twice, you get 0. So it's consistent with Pauli exclusion theorem. So this rho and chi are fermionic variable. On the other hand, x is bosonic variable because the x squared is not 0. Okay. So therefore, here bosonic variable becomes a fermionic variable. Rho and x are fermionic variable. Okay. This delta sends the fermionic variable to the bosonic variable. So this is this is a feature of this transformation. And furthermore, if you apply twice of this transformation, okay, and then del square rho is more like a ds dx chi. However, this is the equation motion. Equation motion tells us this is 0. So variation of L with respect to rho is you get the ds dx. So this is the equation motion. So therefore, del square is equal to 0 up to equation motion. Okay. So okay. So this del square equal to 0 it's called the BRST transformation. Okay. And the important thing is that and then this integral, we already knew that it's everything localized to S is equal to 0. This function is equal to 0. This function is equal to 0, which up here is the fixed point. So which up here is a fixed point. Down row is equal to S of xi is equal to 0. So this is a fixed point of a BRC transmission. And this is the kind of generic feature of the so-called topological quantum field prediction. So the 两次插拢的特点，特点是这个对不动点，就是 fixed point 不动点。The BRC the transformation is I don't know transformation of 不动点 just localized to the all the computation. And the furthermore, so if you try to think this S is the gradient vector field of some function W. Okay, so what we can consider is so suppose so this is just one variable x, but if you consider some something, so I think matrix model here means that it's no longer it's not matrix because it's just single variable. It's just a number model. So number model is that usually action and then Lagrangian is related to the following, as you know, S is equal to dx L, okay, as an notation. But here, so X is a zero-dimensional, so there's no need to do the integral. So action is equal to Lagrangian. So that's what I mean by matrix model. So I should mention. And then you can just generalize the n variable. So that the Si of x is del x I w. Okay. So this is exactly the meaning of gradient flow. So if you have the manifold inside an n-dimensional Rn, okay, and then am I correct? Yeah, I think that's not correct. Yeah, that's not correct. It's not Rn. So here, anyway, so this xi is the local coordinate. I will explain the local coordinate of manifold. And if you take this like this way, you will get the so-called vector field, gradient vector field. So W is the manifold to the R. So this is a so-called Morse function, or height function is okay. Height function is also okay. The height function to nicely perturb it become Morse function. So this is the gradient vector field. Gradient vector field in the of this function W. Okay? And if you plug up into here, the partition function we consider is something like a dx dx dnx, and then square root 2 pi to the n, product of d chi I, d rho I is equal to n exponential minus 1/2, and then you have a debit I square plus chi I down rho I and chi I. You can consider such integral. And then you can use similar BRC transformation, and then what's going to happen is that this transformation is indeed, if you do that integral, this integral, maybe I can erase here. So everything localized to the 0 of this point. So the sum of this gradient vector field is become 0, and if you integrate over the rho and the chi, it becomes the determinant of the down w down x I down xj, and at the point, the boundary because of the percent flow, and sorry, sine of this. Okay, and then here is A. Okay. And this is exactly a Poincare-Hopf theorem, telling that this is called the index of the zero. And then, so more practically, this is called Morse index or Hessian. And this will give you Euler characteristic minus 1. Or Hessian, yeah. This guy is Hessian, and sign of this Hessian is the Morse index. That's what you will get. So therefore, if you use this something called the BRC transformation, or you can just reformulate what I explained by using torus. Using torus, we just send to the height function, and at this point is +1, this point becomes -1, this point -1, this is +1. You can just use this height function to construct these Euler characteristics by a Poincare-Hopf theorem, can be reformulated using this integral, using function variable x and variable rho and the chi, and then you can reform. That's what a bit more sophisticated version of the toy model of the what we did in 1898. Okay. So you learned somewhat the Edward Witten and some grips of the what Edward Witten. Any question at this moment? Okay, so those are just the introduction. And then I'm going to talk about a bit more formal thing from now. It's just the prelude of this class. And I'm going to talk about a bit more formal thing from now. Okay. question at this moment? So if not, I'm going to a bit more talk about oh, by the way, so this when you say t goes to infinity, everything localized this function with zero of this function, or vector field. This is called localization. Localization. That is is it correct? Maybe I is not correct. Is correct. U is this one. Okay. Then I don't know. Now， 我们那我们学习流行的严格定义 manifold。流行的定义。OK， 那定义开始 ，n 为的 n 为流行 n 的定义。So it has number one, has some open covering. It's open covering. And then so which means that the open covering means that there's a manifold like this way. And the U is something like I mean, it's open means something like this one. It's a U1, and then U2, and then so on. So you can just fill out all the manifold by just using open cover. U3, U4, and so on. You just cover everything. All of them. It can be finite in many, or it can be infinite. This is fine. But if you have a compact manifold, you can find many like open sets to cover the manifold element. Number two, there's a map. So this is manifold M, and there's a one open covering here. So I call it the U1. I can map this part into summary Rn into this one. So I call it this one is phi 1. And another thing is another open chart. Each open chart can be mapped onto some different Rn. You can map this one to some open part into E1. Sorry, 5, 2. Okay. Okay. So the continuous and invertible map by alpha So continuous means that the if it is a neighborhood, has to be neighborhood. Okay? You get on like this point is mapped to here, this point is mapped to like somewhere else, something like that. And also environment is a one-to-one map. You cannot have like a 2 points just goes to 1 point, something. You cannot have something. Okay. So number 3 is that the smooth map. So there's an overlap region here. So there's a one overlap region here. Okay. It's mapped to around here. You just want like this. Okay. And then here, so overlap region is U1 cup U2. It's mapped to here. Here, this part is the phi 1. U1 cup U2. And this part is phi 2. U1 cup U2. And then I just want to create a map from like there. Like this one. It's smooth. It's smooth. So this map is the inverse. So that you just bring this one by here by phi 2 inverse because it's invertible. It's invertible, so you can have an invertible map from here to here. And from here to here, you can map like this. Okay. This is alpha beta inverse and phi beta inverse and phi alpha. And in this way, you can map from open set in Rn to open set in Rn. So they're mapped from here to here. But inside Rn, there is a notion called derivative. Okay. So it's a coordinate. So Rn, inside Rn, so manifold is a curve. Okay? It's a curved one. So you cannot have a global coordinate in general, but inside Rn you can have a coordinate. So Rn you can have x1 to xn. Okay? And here y1 to yn. And then so this one is mapped to here. So therefore, you can have x1, y1, xn, y1, yn. On these coordinates, these white region. You can have such map. Then you can just take a derivative with respect to y. So smooth means that you can take a derivative for infinite many times. That's why. Smooth, this map should be smooth means that you can take a derivative. That's why. Okay, that's the. Okay. Okay, and then let's go local coordinate. Let's go coordinate chart. Okay, coordinate chart. Whatever you call it. The collection of these ones is called atlas. And then this function xi it's called local coordinate. So the intuition is that intuition is that so if you have manifold, whatever manifold, and you can have an open patch here, and which can be mapped to Rn. Okay, like this way. And there you have the really, you have a coordinate grid like this way. Okay? So this is the x1 coordinate, this is the x2 coordinate, and so on. You have a grid here. But using inverse map, this can be mapped to like this way. So whatever maybe something like this one. So using this phi alpha, the information of this grid, the coordinate, can be just transformed into local patch. And the same thing can do for other patch. Can map to other. Right? And then this so this is called transition function. Will give you the from red to yellow how to map red to yellow. That's right. Let me give you one example. Sphere. So anyway 抽面，anyway 抽面是的定义是这样的 ，0 u1 inside R n plus 1 where the equal to 1， 抽面。So define the open covering Okay. And then U plus is Sn minus South Pole. U minus is Sn minus North Pole. North Pole is South Pole. Okay. And suppose this direction is U0. Therefore, North Pole is essentially U0 is equal to 1 and U0 equal to -1. And we will do this so-called stereographic projection. Stereographic projection is that you just put the red circle equator here, and then we have Rn is here. Okay. And then we will do the following thing. So here, so U minus, so U minus is something like this one. U minus is something like this one. You just get rid of the North Pole and then you consider the other part. Okay? And so therefore you pick a point on a sphere and just connect North Pole and South Pole, and till it hits the plane Rn that cuts in this equator. Okay? This Rn is just cut this great circle. But this great circle is the dimension is what? This great circle dimension is what? This is Sn, and the great circle should be, yeah. So here, this part is Sn minus 1. I shouldn't call it circle. So this Rn is just cut this Sn into the middle Sn minus 1. Each point of the U minus can just map to the Rn by just connecting North Pole and South Pole and extending. Which can be done, so therefore, the closer to the North Pole, the point is closer to the North Pole, the farther you will get. Okay? The reason why I get rid of North Pole is that the North Pole to North Pole, you cannot draw the line. You cannot draw the line. So therefore, you cannot define a map from the North Pole to this Rn. However, North Poles are included in U plus. Okay? In the U plus case, to do the same thing. We just map from South Pole and the point here, and just connect it like this. Then, in this map, North Pole is mapped to where? North Pole is mapped to South Pole, and North Pole just mapped to here, and it put the origin. And this map can be written like this. Okay. And then this is called stereographic projection. So in Chinese it's called 摄影 projection, stereographic. Okay, so this transition function is called 转移函数。转移函数。我这个时间不是在。函数。transition. Okay. And this is the this local coordinate is called 逐步坐标。逐步坐标。sorry。标。逐。I hope it's okay. 逐步坐标，逐步坐标。And this coordinate is called 摄影坐标，摄影坐标。And then 这个转移函数 can be written as follows. So this. Is 5 inverse 5 is given by x of x squared. X squared. So this function is smooth. So this function is smooth and 1 over x squared x1 dot xn. So like this way. So this transition function is literally what's going to happen from inside. So inside, except north pole and south pole, you just get rid of north pole and south pole. You can define this transition function. So now for and what is 抽面是抽面是 anyway 比如是 it satisfies all the definition. Okay, let's stop here and then we will continue.